Hello, and welcome to Physics for Play. In this episode, we're going to do things a little bit differently. We're going to be talking about the Taylor series, but I'm also going to give you a little bit of personal background on myself. Let's get started. So, I want to talk about why I became a physics major, and the reason I became a physics major was actually because of the Taylor series. If you're unfamiliar with the Taylor series, it's a way of approximating a function around some point A by taking the derivative of that function at that point A and then multiplying by y minus a to some power. So it's a polynomial expansion that gets you an approximation of a function around a point. And we can write out the first few terms of this. Here we're writing f of y around the point 0. And you can see it's just a polynomial expansion. The first term technically has a y to the 0th power, which is just 1. The second term has a y to the first power, which is just y. Then you've got y squared, y cubed, y to the 4th, y to the 5th, y to the 6th, etc. All the way up to y to the n. And if your function is continuous and all its derivatives are continuous, then this is a very good approximation. And if you include an infinite number of terms, you would reproduce the function that you started with. But for practical purposes, you never include an infinite number of terms, obviously. So you usually truncate this after a few terms. And when I first saw this in I forget if it was the first or second semester of calculus in college, I was like, that's kind of neat, but I don't really know how I'm ever going to use that. And then over the summer, I noticed something kind of weird, which is that I had taken physics as a freshman, as we all had to. And if I look at the first equation that you learn, the kinematics equation for position as a function of time, that kind of looks like a Taylor series, right? Your first term is just your function approximated at time 0, Then it's your first derivative at time 0. Well, that's just your initial velocity, times your independent variable, that's at time. Then you've got a 1 over 2 factorial. We've got a 1 over 2 here. We've got the second derivative at time 0. That's just the acceleration, the initial acceleration, times the independent variable squared. That's t squared. So I was like, wait, that looks like a Taylor series. And it turns out it was a Taylor series. There's no physics in this equation, other than to say, objects move in a continuous fashion and they don't go hopping around from point to point. This equation had to be true. And in fact, we can include the third order term that actually has a name. It would be 1 over 3 factorial, or in this case, 1 over 6, since 1 over 6 is equal to 1 over 3 factorial. And the name for the third derivative of position with respect to time is called a jerk. So it's 1/6 j times cubed. And in fact, you can include even more terms. The next 3 terms, and I am not making this up, they have their own names. They go as snap, crackle, and pop. Again, I am not making that up. So we can include an arbitrarily large number of terms, and all of a sudden, kinematics just started to make sense. And I had this weird epiphany that was like, whoa, like, this is just a mathematical description. There's no magic here. All this time I spent struggling in physics, it was all just a Taylor series. There's nothing to worry about. And in fact, if you take a derivative of this Taylor series, you get another Taylor series. You get the velocity as a function of time. Look, it's another polynomial expansion. You've got t to the 0 power, t to the first power, t to the second power, third power, fourth power, fifth power, all the way down the line. And this just seemed like magic to me. Being able to connect these two different things and knowing that there wasn't even any physics here. It was just a mathematical approximation that had to be true. As long as the motion was continuous, this was the equation you were bound to get. And so I came away from that summer just thinking, man, I need to be a physics major because this stuff is so cool. Um, it is it is then perhaps surprising that and a little bit ironic that Brook Taylor ruined my life. Um, Brook Taylor is the one-hit wonder of the physics world. He's got this one equation that we use quite a bit, and I didn't always recognize it. I didn't always recognize it when it showed up in physics, and that caused a lot of problems for me. So this video will hopefully help you recognize it so you will not run into the same problems that I ran into. So where else does the Taylor series show up? So I've gone through my intro physics book, University Physics, and tried to identify what are the equations that are fundamental physics equations and which ones are just Taylor series approximations. And it turns out most of them are Taylor series, even in places where you think, man, this is just physics. No, it's a Taylor series. It shows up everywhere. It's ruined. If you might not think Brook Taylor is ruining your life right now too, but if you're a physics major, he totally is, and I'm going to prove it to you. So why is Taylor out to get you? Okay, well, one of the places it shows up, this one's kind of an obvious one. For any rotating system, if I'm looking at the angle that this wheel is rotating, I would express my angle as a function of time. And that looks a lot like the kinematic equation, and you can see it is in fact a Taylor series. We've got t to the 0th power, t to the 1st power, t squared. Presumably, in addition to angular velocity and angular acceleration, you would also have angular jerk, angular snap, angular crackle, and angular pop if we expanded this out even further. You also get the same thing, again, if you take the derivative for angular velocity. All right, well, that's not too surprising. Where else is Taylor showing up to get you? Well, no, Taylor's out to get you again. You know, we've already talked about Hooke's law in this lecture series, springs. Wait, Santos, you say, that's not a Taylor series, that's a physical law. It's called Hooke's law, it's got to be a law. Well, no physics law here because it turns out this is only an approximation that's valid near x equals 0, much like the Taylor series. And if I include higher order terms in that approximation, you will have x squareds, x cubes, x to the fourths. A real spring gets a force that looks more like this black curve, and we're just approximating it by Hooke's law, which is that linear force term, because linear equations are easy to solve. But a real spring, so I'm plotting a Lennard-Jones potential, which we'll discuss later in the lecture series here. But you can approximate that by using a Taylor series. You'll get something that looks like Hooke's law, which is just going to be a constant times x to the 1st power. And that's only going to be valid in this region where the real spring curve, the black, and the Hooke's law curve, the straight line, line up. All right, what about some other questions? You know, surely gravity is a fundamental equation. Well, F equals mg, one of the first equations you learn in physics, the first force you learn, not fundamental. Newton's law of gravity, we could quibble about replacing it with general relativity. But even in classical physics, F equals mg minus mg is not a fundamental equation. That's a Taylor series of Newton's 1 over r squared law. In fact, we're used to saying the acceleration of gravity is constant at the surface of the Earth. No, it's not. It's totally not. You can, very rarely will you see this, but you can put a first order correction. The rate of gravity, the rate of acceleration for gravity changes as you move up and down further or closer away, as you move further or closer to the Earth. So this is also just a Taylor series. It's just that the mg is what you get when you plug into Newton's laws, when you plug in a distance of that's equal to the radius of the Earth. But Santos, you say, why do all of our measurements of little g, 9.8 meters per second squared, why are they all constant? Well, it turns out that are the actual distance you are from the center of the Earth minus the radius of the Earth is a very, very small number. So this term is almost always negligible. But again, this is just a Taylor series. It's a Taylor series to 0th order. What about Ohm's Law? It's another physics law. Well, guess what? If you actually measure the current that passes through a resistor for a given voltage, it turns out you have corrections to that too. Resistors are rated for a certain range of voltages and currents, and if you go beyond that, guess what? You need a first order correction term. Second order correction term, excuse me. Optics. We've got this index of refraction that tells me how the wavelength changes and also how the speed of light changes when you're entering material. Again, just a Taylor series. We're just truncating the Taylor series at first order, and we're assuming that these other terms, these higher order terms, are negligible. Relativity. I spent my entire freshman first semester physics class thinking that length was just equal to length. It's not. There is, of course, a relativistic correction that tells you that your length doesn't change significantly as long as you're not moving very fast. But if you have a velocity v that's close to the speed of light, all of a sudden your length is going to contract. This is what Einstein's famous for. One of the things Einstein is famous for is length contraction from special relativity. We can, of course, write this out as a Taylor series so that my length is expressed as a polynomial, as a polynomial that includes an expansion of higher and higher powers of that velocity over c term. So I wanted to title this presentation How I Stopped Worrying and Learned to Love the Taylor Expansion. But I just couldn't do that because the truth is the Taylor expansion was just the bane of my existence for 4 years in undergrad and then another 5 years in grad school. But eventually I caught on, and eventually I realized, hey, wait. Anytime you get a physics problem and you see this symbol right here, the much, much greater than or much, much less than symbol, almost always, like 99% of the time, that means you got to do something with a Taylor series. That means you're making some kind of approximation. You're assuming that the variable you're expanding with respect to is small so that as you include higher and higher powers, they become insignificant. So if ever you see the much, much greater than or much, much less than symbol, think of that as a giant Batman symbol in the sky calling out to you, telling you to do the Taylor series. If you take away nothing from the rest of this lecture series and you're a physics major, take away that because it will help you on your problem sets, your homework, quizzes, tests. It'll help you just be a better physicist by seeing what's real physics and what's just an approximation that we're going to use to make our lives easy, because it turns out linear equations are easy to solve. That is all for this time. Join us next time where we'll be showing you how to do the Taylor series expansion using the series command in Mathematica. Like the video if you liked it, and if you'd like to see more, please click subscribe.